So what we said in the previous slide was that at the optimum value under the constraints, we must have that the constraint is tangent to the level line, to one level line of your function, to the lowest level you obtain. And another way to express the fact that they are tangent is just to say that the two gradients have to be collinear. Okay, so the gradient of f and the gradient of g must be collinear. And so a way to write this in math is exactly the following. For an optimum that is localized at some specific point, then there exists a real value lambda such that the gradient of f is equal to lambda times the gradient of g. We're just expressing the fact that they are collinear. Okay, and this is actually what the idea that Lagrange had quite a few centuries ago. And the lambda we've got here is something that we are going to call the Lagrange multiplier. Lagrange multiplier. Okay, so this is it. Now, how do we formalize this? Okay, so we've got same problem. So we want to minimize a function subject to some constraint g of xy is equal to 0. At the optimum value, we must have that the gradient of g is collinear to the gradient of f. Okay, so this is how we can write it. And in order to make it look like a first order condition, because we are already looking at first order derivatives, we are going to define the Lagrangian or the Lagrange function related to the problem. So that's the usual way we write it with a calligraphic L. So it's going to be a function of three variables. So if we had, in our case, two variables, the xy that we're considering, and the lambda that is the Lagrange multiplier, the one we've got here, we are defining this function as our objective function, f of xy, minus lambda g of xy. Okay, why are we doing that? Because if you take the gradient of this, and want to make the gradient of this equal to 0, you will get a first order condition that is actually exactly translated as this. Okay, that's going to be the next slide. Just a small side note, in some books you're going to see used plus or minus lambda. It has absolutely no importance. It's just as long as you're consistent, you can write plus or minus lambda. It's just that we slightly lose the geometric meaning of the Lagrange multiplier. So plus or minus lambda doesn't matter as long as you're consistent. If you make one specific choice, you must keep it for what's coming next. Okay, so let's now write the first order condition that we obtain. Optimization problem. We know we must have that the tangent, the constraint has to be tangent to the level line. It means that the gradient have to be collinear. So that's it. There must exist a Lagrange multiplier like this. The way we express that is we create the Lagrangian function, the Lagrangian, and we just say that we want that we know that at the constraint optimum, we will have that the gradient of this Lagrangian is equal to 0. The gradient, so it has three variables, the x, y, and the lambda. Okay, because my Lagrangian has three variables. So the first, if you differentiate with respect to x and y, you really get exactly that. If you make dl over dx, that's really going to be the d over dx of f of xy minus lambda dg over dx, and we want this to be equal to 0. We make the same thing with y, d over dy f of xy minus lambda dg over dy, it has to be equal to 0. And if we differentiate it with respect to lambda, okay, the lambda that is here, the only thing that we have is g of xy. And if we want this to be equal to 0, that just translates the fact that my constraint is satisfied. Okay, that's just the constraint. Okay, so this is exactly, again, the same thing. Just one small thing that we should note is that saying that the two gradients have to be collinear has a meaning only if the gradient of G is not equal to 0. So this is what is called the constraint scalification. If ever at some point the gradient of G is equal to 0, it means that this point is not qualified to follow the optimization process we are doing. So the point that corresponds to this, well, to an equality where the gradient of G is cancelling, we should study them separately, because if we write this, it has no meaning. Okay, so this is, we make the Lagrangian function. We want the first order condition to find the candidates for optimum value. These are going to be the gradient of my Lagrangian equals to 0, just like for unconstant optimization. These are giving me candidates, and then among those candidates, I have to determine which one are going to be actually the minimum, maximum, and so on. Actually, we only have minimum and maximum in that case, right? And if ever you've got points that are unqualified, meaning where the gradient of G is cancelling, you should study them separately. Okay, just a small look again. When you take the gradient of the Lagrangian, it really has 3 variables. So you will get 2 equations corresponding to expressing the fact that the gradient of f is collinear to the gradient of G. And the last expression, the last equation gives you that when you differentiate with respect to lambda, okay, when we differentiate this with respect to lambda and make it equal to 0, you just get that the constraint is satisfied. Next, we're going to do an example.